I'm happy to talk today a little bit about entanglement and what it means to me. And there's this perception that people have that quantum mechanics is something that's totally foreign from their own daily experience. And particularly entanglement is like this most quintessential quantum mechanical feature. And so people tend to think that that is something that they have no experience with, they can never have experience with. And I guess I want to give my favorite example of entanglement. And that's that if you imagine that you have an atom that's sitting out in space. So a single atom, and that single atom, it's an electron sitting around the nucleus. You might have been taught that the electron is in some cloud around the nucleus, for example, and the electron is everywhere around the nucleus. We'll come back to that in a minute. But anyway, you could take that atom and you could excite it so that the electron is, say, a little bit further away from the nucleus. And if you just let it go, it will decay. The electron will fall back down to its lower energy state, and it'll emit a photon. A photon is just a particle of light, the smallest particle of light. And it'll emit that photon. And so I've got this excited atom out in space, and it emits a photon, and that photon will just go off, and it has to be emitted in all directions, because there's nothing to prefer a particular direction. So the photon is going off in all possible directions, this big expanding spherical wave of where that photon might be. Now, it turns out that photons also have momentum, and we can see that, for example, if you have a comet that's going near the sun, the tail of the comet, the quote tail of the comet, will be pushed away from the sun just by the radiation from the sun, by the light pressure from the sun. So light can exert pressure, so that's because the photons have momentum. So if the atom originally was sitting, when it was excited, was just sitting at rest, and now it gives off a photon, well, we have to conserve momentum. So just like if you, for example, fire a gun, the bullet goes one way and there's a recoil in the opposite direction. If the atom emits a photon, the photon goes in some direction, the atom has to recoil in the opposite direction. Okay, so here's the picture. I've got this excited atom that has decayed. It's emitted a photon that's going off in all possible directions, and the atom is recoiling in every other possible opposite direction. So that is a perfect example of an entangled state between the momentum of the photon and the momentum of the atom. So the photon does not have a definite direction. The atom does not have a definite direction, but they have to be in opposite directions in order to conserve momentum. So that's a perfect example of an entangled state that happens all the time around the universe whenever there are excited atoms that are decaying. Now, I started this by saying that entanglement is something that you can observe. And so now I want to say, let's say you go out at night and you look up at the sky, and you're seeing light from the distant stars. And so there's this atom which is decayed, and it's been emitting its photon, which is in this big spherical wave now. And let's say that you happen to be the person who's looking up, and you happen to be the person that sees that photon. It could have been that it completely missed you, could have hit someone else, it could have hit your hair instead of your eye, but anyway, you happen to be the person that sees it. So a couple things happen. So first of all, you've seen it, so that's great. But that must mean it disappears everywhere else because it's only one photon, so it can only be seen by one person. It would not conserve energy if it could be detected by two different people. So you see it causes it to disappear everywhere else in the universe. Kind of like popping a bubble, when you pop a bubble and then you get like all the juice of the bubble on the thing you popped it with. So suddenly you've removed all that probability everywhere else in the universe. And because it was originally entangled, the photon entangled with the atom, now suddenly the location of the atom, it jumps as though it were moving away from you for the last 100 years. Let's say it emitted the photon 100 years ago. Now suddenly the atom jumps as though it had been moving away from you for that last 100 years. So that's just this sort of non-local effect of entanglement that we sometimes talk about, that when you make a measurement on one thing, it affects the state of the other thing. So whenever you go out at night and you're looking up at the stars, you are constantly popping all these probability bubbles throughout the whole universe, which I think is just like really amazing to think about, that you're affecting all these things going on around the universe by virtue of this entanglement. And I would say that's a genuine, legitimate entanglement.